All right, so here we are into the third section of the chapter now. We've dealt with the idea of properties of gases. We've looked a little bit at gas pressure, and now we're ready to make some applications of those two concepts by starting what we call the gas laws. And our first gas law, known as Boyle's law, is going to relate the pressure and volume of a gas sample. So again, as a reminder, a law in science, particularly in the physical sciences, physics and chemistry, a law tends to be a very short mathematical relationship that's observed across samples. So Boyle's law is so named because the scientist, Boyle, discovered the relationship between pressure and volume and was able to write a pretty succinct formula that describes that relationship. Okay, so what Boyle's law says is that the pressure of a gas is inversely related to its volume when temperature and the amount of the gas, N, number of moles, are held constant. So if the pressure increases, then the volume decreases due to that inverse relationship. Likewise, if the volume increases, then the pressure must decrease. So we see here a movable piston that allows us to change the volume of the container or change the pressure and see the corresponding change. Again, by having that sealed container, we're not allowing gas molecules to escape or to be added, so that's keeping the N, the number of moles of gas, constant. And we're assuming this is all done with no temperature change, so we're keeping T constant as well. Okay, so in Boyle's law, that product of pressure times volume equals some constant value because as pressure goes up, volume goes down a corresponding amount due to their inverse relationship. So the product, P times V, is constant as long as T, temperature, and N, number of moles of gas, do not change. So if you think of a setup similar to those movable pistons from the last slide, if we have conditions where we have initial pressure that we call P1 equal to 8.0 atmospheres, initial volume called V1 equal to 2.0 liters. If we multiply that together, then we get a total of 16 atmosphere liters, or liter atmospheres as is more commonly called. Therefore, if we move the piston in such a way that we double the volume of the container, if we increase the volume from 2 liters to 4 liters, as we see here in the V2, well, P2 would also change correspondingly. Since we've doubled the volume, now we'll take the pressure in half, and we still get that same total value of 16 atmosphere liters, or liter atmospheres. So as this demonstrates, we can see that P1 times V1 equals P2 times V2. Again, 16 atmosphere liters, or liter atmospheres, equals 16 atmosphere liters, or liter atmospheres. So Robert Boyle was able to show this experimentally and arrive at this relationship of P1 V1 equals P2 V2, strictly holding temperature and number of moles constant. So let's take a look now at a guide, right? We've developed these guides pretty much anytime we're solving any problem. Our textbook gives us a guide, and so the guide to using the gas laws, we have a 3-step guide here. First, we organize the data in a table of initial and final conditions, like we saw in the previous slide, the P1, V1, P2, V2 stuff. Second, we rearrange the gas law equation to solve for the unknown quantity. And third, we substitute values into the gas law equation, and then we can calculate that unknown. So in the examples so far, we've known P1, V1, P2, and V2. Ordinarily, we'll be missing at least one, typically either P2 or V2 historically is what will change, or what we won't know and need to calculate. All right, so let's start nice and simple, and we'll show how this stepwise process works out with a particular problem. In this case, we're looking at a sample of nitrogen gas, and remember, nitrogen is a diatomic, so it's N2, and that has a volume of 4.2 liters at 1.0 atmospheres of pressure. If the pressure is decreased to 0.75 atmospheres with no change in the temperature or amount of gas, what will be the new volume? All right, so that's our question. Step 1, let's organize this data into a table where we have initial and final conditions and where we can analyze the problem to see what we might expect. So conditions 1, that we're given both volume and pressure for, the volume is 4.2 liters, the pressure is 1.0 atmospheres. For conditions 2, ultimately we're looking to solve for the volume 2, the final volume. We know that the final pressure, P2, is 0.75 atmospheres. And we also happen to know that in this case, pressure has decreased, so we can predict that volume would increase based on that inverse relationship. So we expect a volume greater than 4.2 liters. We didn't do the math yet, but we at least should be able to, in a multiple choice type question like you're used to seeing on exams, we should be able to eliminate some bad answer choices. We also note there at the bottom that the factors temperature and number of moles have to remain constant for Boyle's law to apply. Moving on here to step 2, we can rearrange the gas law equation to solve for that unknown quantity. So as a reminder, it's the final volume V2 that we're looking for. So we can isolate that by dividing both sides by P2, and then we can flip it, right? Mathematically, we can have the quantities on either side of the equal sign flip places, and so we get V2 equals P1 times V1 over P2, or P1 over P2 times V1 if you prefer. Now finally substituting in step 3, we see that V2 equals 4.2 liters times 1.0 atmospheres divided by 0.75 atmospheres. That gives us a total value. The atmospheres cancel. We're left with liters as a unit, and the numerical part is 5.6. So V2 equals 5.6 liters. Not terribly difficult. Lots of little things to keep track of. Make sure that your units are in there and that they're like units for pressure. We couldn't have combined, say, atmospheres and torr. That would be inappropriate. They wouldn't cancel. Make sure as we get into units that cancel, typically for chemistry, we'll use units of atmospheres. Make sure that your volume's in liters. Make sure that you're doing things in standard unit format. But other than that, everything should work out fairly nicely if you've done your steps correctly. So here's an application of Boyle's law that all of us need to know, or at least need to live, and that is breathing. So breathing consists of 2 phases, right? Inhalation and exhalation. And during inhalation, the lungs expand, the pressure in the lungs therefore decrease, and air flows toward the lower pressure in the lungs. That's very good, right? That's where the airflow needs to go in the inhalation end of breathing. As we consider the other half of breathing, exhalation, during exhalation, lung volume decreases, pressure within the lungs increases, and therefore air flows from the higher pressure in the lungs to the outside. Now, this isn't quite exactly Boyle's law because we are changing number of moles of gas slightly, but and temperature can even change very, very slightly. But again, it's pretty much a great example of Boyle's law in action. Okay, so before we leave chapter 7.3 on Boyle's law, let's have a few learning checks, at least 2 different problems. The first one here, Freon 12 gas, a fluorocarbon, CCl2F2, is used in refrigeration systems. What is the new volume, L, of an 8.0 liter sample of Freon after its pressure is changed from 550 millimeters of mercury to 2200 millimeters of mercury at constant temperature? And again, assuming that we're in a refrigeration system, we're closed. So CFCs, chlorofluorocarbons, are still used in closed refrigeration systems, and if they're appropriately handled and recycled, then not much, if any, escapes into the atmosphere. What they used to be used for in the old days, the 80s and earlier, would be for propellants in like aerosol cans, and that was dangerous because that was definitely exposing the environment to large amounts. So again, they're still in use, but in closed applications like this. And at the end of the day, it doesn't matter that it was Freon 12. What matters is those value changes. Hopefully by now you've already set up your problem. If you've been foolish enough to listen to me blathering on, then why don't you go ahead and pause the video now, apply those 3 steps to solve this problem, and find out the final volume of that Freon sample. All right, so in step 1, remember we're organizing the data into a table of initial and final conditions and analyzing the problem. So here, conditions 1, we know P1 is 550 millimeters of mercury, V1 8.0 liters, P2 is 2200 millimeters of mercury. This time V2 is what we're solving for, and we know that pressure here is increased by a factor of 4, so we expect that the volume will decrease also by a factor of 4, but we're not quite into the numerical end of things just yet. Okay, moving on to step 2, we can rearrange that gas law equation to solve for the unknown quantity. So it's V2 again that we're solving for. This should be familiar to those of us who worked through that example problem. V2 equals V1 times P1 over P2. So we've got the form of it correct, and now we're ready for step 3 to plug in some numbers. All right, and here we have it. We're substituting the values into the gas law equations, and we can calculate. We have V2 equals 8.0 liters times 550 millimeters of mercury divided by 2200 millimeters of mercury. And as I said before, that's a factor of 1/4. And since the pressure increased by 4 times, the volume decreases by 1/4 to give us a final value of 2.0 liters. Hopefully that's what you arrived at on your own. If not, please try some additional problems and certainly reach out to me for help. But all of us are going to try one more problem before we end this section of Chapter 7. All right, so here we have our final learning check. For a cylinder containing helium gas, indicate if cylinder A or cylinder B represents the new volume for the following changes where N and T are held constant. So first, we want to show what happens when pressure decreases. So we're starting at that initial halfway down piston in the cylinder on the far left. So does A or B show what happens when we decrease pressure? And then number 2, which shows a pressure increase result. So pause the video here, take a moment to see whether A or B, which correlates to number 1 and which correlates to number 2 here, and then start the video up and see how you did. Okay, and hopefully you had a little trouble with this one. So it was fairly obvious, I hope, that number 1, where pressure decreases, that correlates to cylinder B, where we increase the volume to decrease the pressure, and therefore we've moved the piston up on the cylinder. Likewise for number 2, to increase pressure, we have to decrease the volume, and that should be cylinder A, where we've taken that initial piston and moved it down to allow for an even smaller volume of gas sample and therefore increase the pressure. So hopefully this chapter 7 section 3 has gone very well and you're following the core concepts. If that's not the case, please do get in touch with me and we'll try to catch you up and clarify any areas that are causing you difficulties. Otherwise, I'll see you in the next section.